Do you know what a burn is? Because if you think you do, hold an ice cube in your hand long enough and prove it. It's not a metaphor. It's not a poetic exaggeration. It's a clinically documented, reproducible, verifiable fact. Hospitals treat ice burns every year. Cryotherapy clinics have specific protocols for liquid nitrogen accidents that produce injuries indistinguishable from a flame. And before you say, "Oh, but that's different," no, it's not. And you're going to understand exactly why it isn't. But what exactly is a burn? The mechanism you're picturing is wrong in a way that matters. And it's this flawed definition that stops you from seeing how ice can cause the same damage as fire. Feynman had a quote I like to remember whenever I think I understand something. He said, "I think I can safely say that nobody understands quantum mechanics." But he wasn't talking about quantum mechanics. He was talking about the human habit of confusing familiarity with comprehension. We know words. We use concepts. We think we know what hot is, what cold is, what a burn is. But do we? In this video, you're going to understand the real mechanism, and it'll change how you think about temperature, sensation, and damage. You'll learn the method Feynman used to dismantle everyday physics, including an answer that's probably wrong in your child's textbook right now. And by the time you leave here, the absurd question in the title will make perfect sense. Not as a fun fact, but as true comprehension. Let's start with the definition that's wrong. You think it's when something hot comes into contact with your skin and causes pain and damage. Right? Not exactly. And the inaccuracy in this definition is what's going to open up the whole conversation. Let's get straight to the biology. A burn, at the cellular level, is a specific event. It's the destruction of proteins, the rupturing of cell membranes, and the triggering of an inflammatory cascade. That's a burn. Not the heat itself, the damage heat causes. Think of proteins as incredibly precise, three-dimensionally folded structures. They maintain this shape because they have specific chemical bonds that rely on precise conditions of temperature, pH, and molecular environment. When you apply excessive heat to a protein, these bonds break. The protein loses its shape. It loses its function. This is called protein denaturation. Ever seen an egg white turn white when heated? That's denaturation. The albumin proteins, which were transparent and folded in a specific way, lose that structure when heat breaks the bonds. The process is irreversible. You can't unburn an egg. The exact same thing happens to the proteins in your skin cells when you touch an intense heat source. The proteins denature. The cell membranes, made of precisely organized lipids, rupture. Cellular contents leak out. The immune system detects the chaos and launches an inflammatory response. Swelling, redness, pain, blisters. That is a burn. And now, pay attention to what didn't appear in that description. Heat. Heat is the most common trigger. But it's not the mechanism. The mechanism is rapid cellular destruction. And rapid cellular destruction can be produced by triggers other than heat. Here's the twist. Protein denaturation doesn't need heat. It needs a rate of energy transfer that exceeds the cell's ability to keep up. An intense electric field destroys proteins. Certain chemicals destroy proteins. Extreme mechanical pressure destroys proteins. And here's where this is going. Extremely low temperature does the same thing. The word burn created a semantic trap. It makes you think fire, heat, red. But what the body actually calls a burn is rapid and irreversible cellular damage. Extreme cold does exactly that. So the question is no longer, how can ice burn? The right question is, given that a burn means rapid cellular destruction, why do we assume that only heat can do it? The answer lies in how your nervous system is built. Here's a fact that'll rewire how you think about sensation. Your body doesn't have a thermometer. You don't have any sensor that measures temperature in degrees. What you have are damage detectors and threat detectors. They are different things, and that difference is the heart of everything we are discussing. Let me explain the real mechanism. In your nervous system, there are specialized sensory neurons called nociceptors, from the Latin nocere, to cause harm. They detect stimuli that threaten tissue integrity. Among these nociceptors, there are thermoreceptors, neurons that respond specifically to temperature. And here's the key. Thermoreceptors don't report temperature. They report a temperature deviation that represents a threat. Inside the thermoreceptors, there's a specific protein called TRPV1. Its full name is Transient Receptor Potential Vanilloid. 1. An ion channel that acts as a molecular switch. When something activates TRPV1, it opens. Calcium ions enter. The neuron fires a signal to the brain. Alert, potential damage, body region X. What activates TRPV1? This is where it gets interesting. TRPV1 is activated by heat above 43 degrees Celsius. That's the temperature at which tissues begin to suffer real damage, and it's no coincidence. Natural selection calibrated the sensor right at the danger point. TRPV1 is also activated by capsaicin, the active compound in chili peppers. Capsaicin fits into the receptor like a key in a lock, opens the ion channel, and fires the exact same dangerous heat signal. No actual heat needed. This is why peppers burn, literally. Your nervous system sends a burn signal because capsaicin triggered the heat damage sensor. And now, the revelation that makes the title of this video literally true. TRPV1 is also activated by extreme cold. When tissue temperature drops into dangerous ranges, usually below 10 degrees Celsius, or in rapid freezing, TRPV1 wakes up. The very same channel that screams burn when you touch a hot pan starts screaming burn when you hold ice for too long. This isn't a neural metaphor. It's the exact same channel, the exact same signal, the exact same firing. From your nervous system's point of view, peppers, fire, and sufficiently cold ice all produce the same warning: cellular damage in progress. There's an important parallel receptor, TRPM8 transient receptor potential. Melastatin 8 responds to cold in the comfortable range, below 25 degrees Celsius. It's also activated by menthol, which is why menthol products give you that cooling sensation without actual cold. TRPM8 was built to detect moderate cold, and menthol tricks it the same way capsaicin tricks, TRPV1. But below a critical threshold of cold, when the tissue is genuinely at risk, TRPV1 takes over. And TRPV1 only has one message to send. The evolutionary logic is elegant. The nervous system wasn't built to report temperature with precision. It was built to detect tissue damage and trigger a protective response. Both excessive heat and excessive cold destroy cells. Same warning system covers both extremes. Your brain doesn't receive a temperature reading. It receives a signal. Cells are being destroyed right here. The signal for cell destruction by extreme cold is reported to your conscious brain as a burn, because that's exactly what's happening. You've just seen the nervous mechanism. But knowing that TRPV1 fires doesn't explain why cellular damage happens the same way at both extremes. For that, we need a method that will unravel an answer that is probably wrong in the textbooks you used in school. We need Feynman. Richard Feynman won the Nobel Prize in Physics in 1965 for his development of quantum electrodynamics. But what made him Feynman wasn't the Nobel. It was his obsession with the difference between knowing and understanding. He had a test he constantly used on himself and his students. He called it distinguishing between knowing the name of something versus understanding something. The distinction seems obvious until you try to apply it. Here's the test in practice. You know magnets attract metal. You probably know it happens because of a magnetic field. If someone asks why, you say magnetic field and feel like you've answered it. But Feynman would say, that's not an answer. That's changing the subject. The question was, why does the magnet attract metal? The answer, magnetic field, just names the phenomenon. It doesn't explain the mechanism. So he forced the chain of whys. Why is there a magnetic field? Because electrons in iron have aligned spins. Why do aligned spins create a field? Because spins produce a magnetic moment. Why does a magnetic moment produce attraction? And here, very quickly, you hit quantum mechanics. In quantum mechanics, you hit axioms, fundamental rules that don't have a why beneath them in our current state of knowledge. Feynman loved this moment, not because hitting a limit was depressing, but because forcing the chain of whys exposed how many answers were just labels, not explanations. That's the Feynman method. Ask why until you hit bedrock, whether it's a confirmed physical law or an honest limit of human knowledge. You can't stop just because the answer sounds familiar. Familiar isn't the same as correct. Feynman applied this method to everyday physics constantly. Whenever someone said they knew how something worked, he tested it. With surprising frequency, he discovered the answer was just a label over a flawed mechanism. There's a classic example, one you've probably accepted as truth, one that's probably wrong in your textbooks. Why is ice slippery? Here's the answer you probably learned. When you step on ice, your weight creates pressure that melts a thin layer, forming a film of liquid water that lubricates it. Sounds reasonable. It's in textbooks. Most teachers teach it, and it's fundamentally wrong. Let's do what Feynman would do. Check the numbers. To melt ice through pressure, you need a drop in the melting point. The ice-water equilibrium curve has a negative slope. Extra pressure favors liquid water. Technically, pressure can lower the melting point of ice. How much? Here's data most people never check. You need roughly 13 megapascals of pressure to lower the melting point by just 1 degree Celsius. 13 megapascals for 1 degree. Now let's calculate what an ice skater applies. A 70 kilograms person on a blade with a contact area of about 1 centimeter, already a generous estimate generates roughly 7 megapascals. That lowers the melting point by less than 0.5 degrees Celsius. On an ice rink at 10 degrees Celsius, you'd need over 130 megapascals to melt ice by pressure. A person on a blade doesn't come close. Walking normally with the entire sole of your shoe? Even lower pressure. Ice is still slippery. The pressure melting theory doesn't explain why you slip on an icy sidewalk in sneakers. It doesn't explain ice at 30 degrees Celsius. It doesn't explain why an ice cube on a table is slippery when you touch it lightly with your finger. So what really explains it? In 1842, almost 30 years before Einstein was born, Michael Faraday noticed something strange. 2 ice cubes pressed together would stick to each other, even well below freezing. He proposed the ice surface had a special layer and intermediate state between solid and liquid. He was right. Experimental confirmation came in the 20th century, but Faraday had identified the correct phenomenon, the quasi-liquid layer, or pre-melting. The ice surface isn't identical to the inside. At the interface between solid and air, water molecules are organized differently, less rigidly bound, more mobile. This creates a molecularly thin layer that behaves between liquid water and solid ice. This layer exists at 30 degrees Celsius. It exists regardless of pressure. It's an intrinsic property of the ice surface. This layer lubricates. This is what makes ice slippery. This isn't minor curiosity. It's the difference between an explanation that sounds right and one that actually is right. The pressure melting theory spent decades in textbooks because no one checked the numbers. No one asked, how much pressure do you actually need? No one pulled a Feynman. Textbook ice is the perfect example. But Feynman went further. He applied this exact same method live, with consequences that changed history. On January 28, 1986, the Space Shuttle Challenger exploded 73 seconds after launch. 7 astronauts died. The cause was an O-ring-A rubber seal that lost its elasticity in the cold morning. Feynman was on the Rogers Commission to investigate. He was the only physicist among lawyers, bureaucrats, and NASA managers. He was frustrated by vague testimonies and evasion of responsibility. During a nationally televised hearing, Feynman pulled an O-ring and a glass of ice water from his pocket. He put the ring in the water a few minutes, took it out, squeezed it. The material had completely lost its elasticity. The demonstration lasted less than a minute. Feynman didn't need 200 slides. No computer models. Ice and rubber showed, in real time, that rubber at near freezing temperatures loses the properties necessary to seal a rocket. The most watched experiment in the history of public physics was a professor with a glass of ice water. This is the Feynman method with real-world consequences. Not asking, does this work in theory? But what are the numbers? What happens in practice? And what does physical reality say? Now, with this method in hand, let's see what happens to cells when ice meets them. A trained dermatologist looking at a second-degree wound can't distinguish whether it came from a flame or liquid nitrogen. This isn't rhetoric, it's clinical fact. The lesions are morphologically equivalent. Hospitals treat cryogenic burns using the exact same protocols as thermal burns because the tissue damage is exactly the same. But why? Imagine observing a single skin cell the moment it touches liquid nitrogen. What happens in milliseconds is indistinguishable from a cell touching a flame. Let's zoom into the molecular scale. When a cell's temperature drops below freezing, the water inside begins to crystallize. Simple concept, devastating implications. Ice crystals occupy more volume than liquid water. When they form inside a cell, they expand. The cell membrane, a precarious, highly organized lipid structure, can't withstand it. It ruptures. When the membrane ruptures, intracellular content leaks out. Proteins, organelles, DNA, ions, everything spills into extracellular space. The cell is dead. The immune system reads the leaked material as damage and triggers an inflammatory cascade identical to thermal burns. There's more. Even without ice crystals, in less extreme freezing intense cold, causes protein denaturation directly. Heat breaks bonds that maintain protein structure. Extremely low temperatures alter van der Waals forces and hydrogen bonds, collapsing the protein structure. Enzymes stop working. Ion pumps fail. The cell can't maintain the electrical balance that keeps it alive. Notice the pattern? Cell death from cold and heat follows the exact same biochemical pathways. Protein denaturation, membrane rupture, enzymatic failure, inflammatory cascade. The mechanism is identical. Only the direction of energy transfer differs. Both thermal and cryogenic burns are cellular destruction caused by energy transfer so rapid it overcomes the cell's repair capacity. Heat? Energy enters too fast. Extreme cold? Energy drains too fast. The biological result is the same. That's why cryotherapy clinics have strict protocols. Liquid nitrogen at 196 degrees Celsius doesn't just cool you down. It causes third-degree cryogenic burns on prolonged contact, indistinguishable from flame burns on biopsy. Documented cases of severe cryogenic burns from poorly administered cryotherapy are treated in burn units like any severe thermal injury. Frostbite superficial tissue freezing starts, causing damage between 2 degrees Celsius and 10 degrees Celsius. The skin turns red, edema forms, blisters appear. Treatment involves gradual rewarming, tissue protection, and inflammatory management opposite of thermal burns in applied temperature, but clinically identical protocol. Cold burns. Not metaphorically. Literally, at the cellular level, extreme cold produces exactly what heat does. Irreversible cellular destruction from energy transfer beyond tolerance limits. The cellular mechanism is settled. But here's an open question. If this is real and verifiable, why does our intuition resist it? Why won't the brain accept it? You're the product of a few million years of evolutionary selection in a specific environment. That environment had a very narrow temperature range. Human ancestors lived primarily in tropical and subtropical Africa. Temperature variation that mattered for everyday survival was about 0 degrees Celsius to 50 degrees Celsius. Even that's optimistic. Most experiences happened between 10 degrees Celsius and 40 degrees Celsius. The human sensory system was calibrated for this specific range. Below 10 degrees Celsius, the nervous system fails. Nerve conduction becomes compromised. Temperature perception becomes less accurate. Paradoxically, people in severe hypothermia start to feel hot when their lives are at risk. The detection system flips. Above 50 degrees Celsius, damage happens so fast, sensory information barely processes before damage becomes severe. The vocabulary we use for temperature hot, cold, warm, freezing, burning, icing was developed for the relevant sensory range. These words carry implicit assumptions. Burning implies heat. Freezing implies cold. Words have built-in polarity, and this prevents us from seeing that extremes in both directions produce the exact same cellular event. Feynman talked about this constantly. Language deceives us because words were built for ordinary situations. When you go to extremes, very high or very low temperatures, near light-speed velocities, or subatomic scales, ordinary language fails. It carries built-in human-scale intuitions. That's why physics needs mathematics. Not because mathematicians are smarter. Mathematical language was built to be precise at any scale, without intuitive assumptions. And here's where Kelvin's insight comes in. Imagine two identical cubes on a table. Iron at room temperature and ice. Place your hand between them without touching. Intuitively, you feel cold from the ice. But the cold didn't come from anywhere. The ice particles, moving slowly, were ready to absorb energy from faster air particles. Your nervous system interpreted this probability of energy loss as cold. No substance moving, just a difference in molecular speed. The Celsius scale was built for humans. 0 is freezing, 100 is boiling. Convenient for cooking and climate. But it tells us nothing about what temperature actually is. The Kelvin scale starts at absolute 0 where all molecular agitation stops. 0 Kelvin is 273.15 degrees Celsius. This scale matters because it reveals temperature isn't a property of objects. Temperature is the average kinetic energy of a system's particles. When you say something is hot, the particles are moving fast, vibrating, spinning, translating with high kinetic energy. When you say something is cold, the particles move slowly. 0 Kelvin would be complete molecular pause, something quantum mechanics says never perfectly happens. This dissolves the paradox. Cold doesn't exist as an independent entity. There's only less kinetic energy. When an object with much less kinetic energy touches living tissue, the object's particles absorb energy from the tissue systems in thermal disequilibrium balance by transferring energy from more energetic to less energetic. That's the second law of thermodynamics. Ice doesn't emit cold. Ice absorbs energy from your cells. If it absorbs too fast, if energy drainage exceeds the cell's ability to maintain themselves, cellular damage occurs. Ice crystals form. Membranes rupture. Proteins denature. The phrase ice burns isn't rhetorical. It's more accurate than ice just freezes. The physical process is energy transfer so rapid it destroys tissue. Tissue destruction through energy transfer is exactly what a burn is. Temperature isn't a static property. It's the average kinetic energy of a system's particles. When two systems with different temperatures touch, energy flows from more energetic to less energetic, hot to cold, in everyday language. What cell biology shows is that final temperature doesn't matter for tissue damage. It's the transfer rate. It's how fast energy enters or leaves tissue relative to the cell's capacity. Think of it this way. A living cell constantly spends energy to maintain itself. Ion pumps running, proteins being synthesized and repaired, electrical gradients maintained. The cell has a maintenance rate. If ambient temperature changes gradually, the cell adjusts. If energy transfer is too fast, whether excessive heat entering or heat draining from extreme cold, the cell can't keep up. Damage results. The paradox how ice can burn seems like one only because language creates false polarity. Hot burns, cold freezes. That's a simplification that works in normal sensory range and fails at extremes. Real physics has no polarity. Real physics says, when energy transfer rate exceeds biological tolerance, there's cellular destruction. Transfer direction energy in or out doesn't affect the cellular outcome. This is where the Feynman method delivers its greatest gift. It didn't just correct the answer about ice and burns, it gave you a framework. Whenever a paradox seems impossible, the language is probably wrong, not the physics. Check the terms. Check the definitions. Ask what the words actually mean mechanically. Burn seemed to mean damage by heat. It means cellular destruction by energy transfer that's too fast. Correct the term, and the paradox dissolves. Temperature seemed to be a quality of objects. It's the average kinetic energy of particles. Correct the concept, and ice drains energy from cells just as factually as fire injects it. The universe doesn't organize phenomena for human intuition. Hot and cold aren't fundamental opposites. They're points on a kinetic energy continuum. At the extremes of that continuum, human cells meet the same fate. Destruction too rapid to repair. So, does ice burn? Yes. And now you know exactly why not as trivia, but as true understanding. What changed wasn't the fact. The fact was always true. What changed was the framework. When you stop thinking of temperature as a quality of objects and start thinking of it as kinetic energy and transfer rate, the paradox disappears. Not because you memorized a new answer, but because the wrong question became obvious. That's the Feynman method. It's not exclusive to physicists. It's a habit of thought you take away from this. Before accepting an explanation, check if it's a label or a mechanism. When a paradox seems impossible, the paradox is probably in the language, not in the universe. Faraday arrived at the correct mechanism in 1842 through careful observation and refusing to accept the obvious explanation. Feynman concluded a national investigation with a glass of ice water. Not because they had better tools, because they asked different questions. If this way of exploring physics makes sense to you, the next video applies the same method to another phenomenon almost everyone explains incorrectly. Subscribe so you don't miss it.